would like to invite up Paul Staten. And the topic of his presentation is improving stratospheric gravity wave tomography from GPS radio occultations.
There we go. Hi, this is the first of two gravity wave talks you're going to be hearing today, and I'll try to set things up for Yu Wang to talk to you about gravity waves from hurricanes. So I'm looking at GPS radio occultation data and how to determine the horizontal length scale and propagation direction or wave angle of gravity waves, or in other words, their their zonal and meridional wave numbers, K and L. And the trouble with GPS RO, of course, is that compared to the atmosphere, RO profiles pretty much go straight up and down. So you can get the vertical wave number M really easily, but getting the horizontal wave numbers is a little trickier. You need 3 profiles instead of just 1. And you traditionally need these profiles to be close together and effectively simultaneous. So Thorsten Schmidt set the limit to 15 minutes when Cosmic 2 was first launched. And since the satellites were close together, he was able to do gravity wave tomography with Cosmic 2 until the satellites separated. But as they separate, you need to loosen up a little bit. So Joan Alexander's used a little bit looser collocation requirements and giving you 5 more minutes. Later in today's talk, I'm going to show you some preliminary results with data that are separated by as much as 4 hours. And that's one of my goals, is overcoming this simultaneity constraint. And so you take these 3 profiles, they have to be close together. You do a wavelet decomposition of the 3 profiles. So it's like a Fourier analysis, but you get a decomposition by frequency or wave number, but you also get it at each level. And after you decompose it, that gives you the wave amplitude for each wave number and the wave phase for each wave number at each altitude. And then from the zonal and meridional wave numbers that we'll talk about in a minute, and the meridional wave number you get from this decomposition, you calculate the gravity wave momentum flux for each altitude and each wave number, add those together to get the net flux for your profile. And so to get wave number K and L, you look at the 3 profiles, you pick some altitude, and you compare the phase difference between pairs of profiles with the zonal and meridional spatial distance. And since you have 3 profiles, or 2 pairs centered around profile dot on the left there, that gives you 2 equations for 2 unknowns. It's a simple linear equation, so you solve it and you're done. You get K and you get L, and bam, you've got your horizontal length scale and direction for the gravity waves. And it's simple, it's fast, but again, the triads or triplets have to be within tens of minutes of each other. And so if you have like a whole day of Cosmic 2 data, like here in December 31st, 2020, you've got 2 triplets that meet the looser Alexander criterion. Also, the finite wavelet analysis, the decomposition there, can sometimes step over the actual physical vertical wave number, and you get a little spectral leakage, which I'm still working on. The wave direction is ambiguous to the sign because you got a portrait of the waves, but they could be going one of 2 directions. It's susceptible to aliasing, meaning in particular, since the waves can propagate during the minutes between profiles, the wavelength will look different than it actually is. And then it's difficult to evaluate the goodness of fit of this. Typically what we do is we calculate the wave numbers. They sound good. You calculate the wave flux, the momentum flux. It also looks good. It's hard to verify. And that's about as good as we can say with the methods we've got. But the ambiguity of the direction is something that Peter Alexander worked on a while back. In 2018, he said, well, why don't we just add a 4th profile, same position as one of the others, but a little later or earlier in time? We can use the other 3 profiles. Other 3 profiles to get K and L. And then once we have K and L, we can use this other profile to get omega, the temporal frequency. And to get the vertical wave number M, instead of doing a decomposition, they just use 2 points in the vertical. That becomes a little important here in a minute. one thing I really like about their paper is that they proposed a way to evaluate their fit. This paragraph quote at the bottom is the only thing they say in the paper, so I have a hard time reproducing it, but I think what they're doing is they look at the different solutions they come up with because they get branching solutions, and they see which solution most closely matches the dispersion relation for gravity waves. I love that idea. So I take it a little further here in a minute. So they overcome the direction ambiguity with that fourth profile, but they have a fourth profile. And in their paper, they say like, yeah, we can't use this for real data yet because we don't have enough observations. Even with ROMEX, I still don't think we can get 4 profiles and still meet, say, the Schmidt criterion for 3. Also, since they're not decomposing, they can only get 1 wave per profile. But I think we can do better. I don't think we need a 4th profile because these are gravity waves we're dealing with. And so why don't we take the dispersion relation for gravity waves and use that to eliminate omega and express it in terms of K and L, our 2 unknowns from before. Now we have F and N, the Coriolis and Brunt-Väisälä frequencies, but those are easy to calculate. We can treat them as constant for the rest of today. And so now we have 2 equations, again with 2 unknowns. I put a minus sign in front of the square root instead of a plus or minus, because there's that directional ambiguity, the waves I mentioned earlier. And this is because gravity waves in the lower stratosphere, typically their group velocity is upward. They're propagating energy upward from terrain or from clouds, so they propagate downwards, their phase velocity is downward. And that, in as much as that's true, that actually solves the direction ambiguity problem for us. And so 2 equations, 2 unknown, they're not linear. So the solutions are a little bit messy. So we do a little bookkeeping. All the differences between variables, we just label A, B, C, D, E, F, G, and H. And with that bookkeeping, then you start solving it and it gets worse and worse. And 3 or 4 pages into it, you decide I'm going to use a symbolic math solver in Python. And I did, and it worked great. It agreed with my work so far. And those are the 16 equations right there. I'm not sure if you can read those, but if you zoom in a little bit, you'll see that they basically differ by like the sign of some of the terms because you have that square root in there. So there are 16 solutions differing by 3 sets of signs. But you have 16 solutions. What do you do with them? How do you pick the right one? Well, thinking back to Peter Alexander's work, we see which one fits the best. So we construct a gravity wave based off of the K and the L and the A and the M from the vertical decomposition. And then we fit this gravity wave to the 3 profiles. We plug in X, Y, and Z at every point in the 3 profiles. And then we calculate the root mean squared difference between this modeled wave, these 16 modeled waves, and the 3 temperature profiles. And whichever K and L set gives us the smallest root mean square error, we take that solution. But how well does it actually work? Well, if we simulate a bunch of waves, and since we simulate them, plane waves, we know their phase perfectly, and we've just looked at their phase, well, we can skip the vertical decomposition stage and go straight to the phase, straight to the algebra problem. So let's see how well the algebra part works. So here on the left, we have a bivariate histogram. We run it like 10 or 20,000 times, 10 or 20,000 random profiles fitting a pretty typical distribution of gravity waves. And the green curves here are the traditional method. And as you can see, the bivariate histogram is centered around the crosshair in the middle. The crosshair is the truth of these waves that we're generating. And the orange curves are this expanded algebraic approach. And you see that the orange distribution is much tighter. Now there's some gunk on the, let's see, top left and bottom right of that profile. That's the bottom contour level. The green contour level that looks junky like that is off the chart. So these are bunched much tighter. The purple is an approach I was trying a year ago that was doing random walking in K and L space until you find the best fit. And it works pretty well here. If we loosen things up a bit, like John Alexander did, you can see that the simultaneity constraint is a little bit broken, so the green solutions are spreading out quite a bit, but the orange and purple are still nice and tight. But since we account for differences in time now explicitly, let's go ahead and let these profiles be separated, not just like a quarter wavelength, but a quarter period apart. And, ooh, all right, so the simultaneity constraint is gone, so the green method is just completely destroyed now. But the orange is still looking really good. And there's that random walker, that purple one. The random walkers are going off. I don't know where they're going, so we're not going to worry about that approach anymore today. We're just going to compare the traditional and the expanded algebraic approach. But this is if phi is known, and radio occultation profiles don't measure the phase of gravity waves. They measure bending angle refractivity and get temperature retrievals. So let's simulate these temperature profiles. Let's simulate some temperature perturbations corresponding to plane waves. And let's go ahead and do that vertical decomposition step to get the phase first. Now things look a little bit messier. The errors have increased a little bit. We still have that green traditional method centered close to that the crosshair. It's biased a little bit short with a wavelength. But the orange, the expanded approach is right on for the Alexander collocation requirements. In the middle panel now, I've got a histogram of root mean square errors, and you can see that the traditional approach has a root mean square error close to 1 Kelvin, and this new approach has a root mean square much closer to 0. Now, if we loosen things up to that 4-hour requirement again, the traditional approach falls apart, and this time the expanded approach is biased long, but it's kind of a systematic bias. I wonder if we can remove that. But if you look at the errors for it, the root mean square errors, in other words, how well it's fitting the observed profiles, it's fitting these profiles almost as well as the traditional approach that's currently being used is currently fitting profiles that are much closer together. This is great. This means that there's hope that we can extend that time period by a few hours, and instead of getting 2 or 3 profiles or triplets per day from Cosmic 2, we would get about 200 from Cosmic 2. Now, if that's just Cosmic 2, imagine what this would do with ROMEX. We'd go from, I'm guessing, dozens of triplets per day with ROMEX to maybe 1,000, maybe 2,000, because if you double the density of the measurements, you more than double the number of triplets. So I'm excited to go to ROMEX next, because I could probably just take 1 day of data and start looking at maybe a map of wavelength or flux. As is, I had to go with a month, and the results are messy. I went with the 4-hour collocation requirement, the traditional method on the left, which shouldn't work for 4 hours, so it's not a very good, it's an upper bound, but it's a very loose one. And the right had the expanded approach. The top row there is the root mean square errors. The 2 panels look basically the same, but the dots on the right are darker, so it fits the profiles better, as we'd expect. And it's doing so using shorter wavelengths than the traditional approach is in this case. And so if the horizontal wavelengths are shorter, your gravity wave momentum flux is a little bit bigger, so you have more yellow dots at the top. And the directional ambiguity is gone, so we can get the directional flux, and the directions look like they're kind of all over the place, salt and pepper. So I'm really excited to fix this some more, work on some more, and apply it to some ROMEX data and see what we see then. And I'll leave this up for you, and thank you for your time.
Thank you, Paul. That was a very nice mathematical elegance for gravity waves. So I would like to open the floor for questions. We have about 2 minutes, maybe 1 or 2 questions.
Can you actually comment on what happens to your determinations of directions and wave numbers if you have a spectrum of waves present?
Yes. The Parseval's theorem states that the energy summed over the times when you do a Fourier decomposition should match the energy summed over frequencies. And if you're just looking at the amplitude of the waves for a single profile, and if your profile is decomposed nicely, that means that you can have multiple wave packets and the total variance will be correct. There are a couple of problems that I'm hitting. One is that if your decomposition doesn't work out real nice, you have spectral leakage. And also when you take, say, like 2 wave packets and it sees them as 1 packet, all of a sudden your horizontal wavelength determination gets thrown off as well. So to avoid spectral leakage, what I have done is I take the profile, when I decompose it and decompose it again, decompose it again, decompose it again, but cutting part of the profile off every time. And so what happens is that the decomposition is hitting different vertical wave numbers every time. And I do that until I get the largest amplitude wave at the level I'm looking at. So if you think about a decomposition, wavelet decomposition, Stockwell transform, you have the wave number and height, you get kind of a smeary Gaussian shape around wave packets. So if you find the maximum, you're hopefully hitting the center of one of those wave packets. So if I can find the center of one of those packets, then I can decompose the wave and hopefully isolate that particular wave. And then I can remove one of my ideas to do next is to remove that wave from the temperature profile and then do the decomposition again and hopefully isolate the other waves. But even just one wave packet, if it's divided between two neighboring wave numbers, even one wave packet can cause trouble with that. So yeah, it is hard. Thanks.
Thank you, Paul. I would like to invite the next speaker up, Ayodan Sweeney. And the topic of the presentation is about investigating the anomalous